Hi everyone, my name is Orestis Papadigiannopoulos and I'm going to talk about learning to maximize welfare with a reusable resource. This is a joint work with Matthew Fo, Konstantin Karamanis and Sanjay Sakotai. Our main motivation is gig economy. So gig economic workers can be ride-sharing drivers, delivery drivers, or crowdsourcing workers. And generally their goal is to decide whether to accept a task and collect a reward or skip on the task. And in case of acceptance, the worker becomes busy for a short time period. And in many applications, busy periods have fixed duration. For example, an hour, a day, or a week. And the problem of each individual worker is to decide whether to accept a reward or reject a given task. And motivated by this, we consider the following problem. We consider a sequence of n IID rewards, which correspond to requests of fixed duration. And the decision maker observes at each round the realized reward and decides whether to accept the reward and become busy for the subsequent D rounds or reject the reward and remain available for the next round. We assume that the busy time D is known, but the time horizon N is unknown to the decision maker. And also we consider two cases. The one is that the reward distribution is known to the decision maker a priori, and the second is that we learn the distribution. And the goal is to maximize the total expected reward collected, and specifically relative to the expected reward collected by a prophet who knows all the realizations a priori and has infinite computational power. Let us first consider the case of known reward distribution. For large or infinite time horizon, it is natural to assume that a fixed threshold policy should be reasonable. In the sense that an algorithm might compute a threshold as a function of the reward distribution and the delay. And then at each round, if the resource is available, if the worker is available, and the realized reward is greater than the threshold, then we accept, and otherwise we reject. So what we want is to guarantee that the expected reward collected by such a policy is close to that of a prophet. And there are two questions here. The first is how to define this threshold. And the second, can we even characterize the prophet's expected reward? And we start from an infinite dimensional LP relaxation. And this relaxation, Q of X, is the set of variables where its Q of X is the fraction of time where reward X is collected in an optimal solution. So for the second set of constraints, let this be the probability mass function of the reward distribution. The second set of constraints says that the fraction of time where a reward can be collected is definitely smaller than f of x, is less than a specific reward, always less than the probability that a specific reward can be realized. And the first set of constraints suggests that the total area of Q of x is at most 1 by d plus 1, which is reasonable because if we know that collecting a reward blocks the worker for D rounds, we know that we cannot collect more than a fraction of 1 by d plus 1 of the rewards. And the first claim is that we prove is that this LP essentially yields an upper bound on the prophet's expected reward up to some small additive errors. And further, we observe that an optimal solution to this LP can be computed by greedy water filling, which means that starting from the largest possible value, we start matching f of x. We set Q of x equal to f of x up to the point where the first set of constraints become tight. So the total area is exactly equal to 1 by d plus 1. In that case, and therefore we can see that the optimal solution, Q star of x, is equal to f of x for x greater than some tau, where tau is the quantile, the 1 minus 1 by d plus 1 quantile of the distribution, and 0 otherwise. And further, the optimal value of this LP is equal to n times the expected reward conditioned on the fact that this reward is greater than tau. Now, motivated by this, we consider the following natural algorithm. Essentially, we set a threshold offline. We set a threshold tau, which is equal to the 1 minus 1 by d plus 1 quantile of the distribution. And at each round, we first observe the reward, And if the reward is greater than the threshold and the resource is available, the worker is available, then we collect the reward and make resource unavailable for the subsequent D rounds. And otherwise, we skip on the reward and move on to the next round. And now let us try to analyze the competitive guarantee of this algorithm relative to a profit. So fixing any round T, this algorithm collects in expectation X sub T times the indicator of the event that this reward, X sub T, the realized reward is collected, which in turn is a factor of two things. The first is that the reward has to be over the threshold, and the second is that the resource should be available. And notice that the availability of the resource is independent of the realized reward of the same round because it only depends on the past. And therefore, we can break this product into these two factors. But now, what is the probability that the resource is available at any round T? By fixing a threshold, we can essentially study the system and model the system as a Markov reward process, where its state of D+1 states, where its state represents the number of rounds until the resource becomes available again. And so, for example, our system starts from state 0. Let's say that we observe a reward which is over the threshold. We move to state D, and then for the subsequent D round, deterministically, we move back to state 0, where we are again available. And then we observe another reward, which is maybe smaller than the threshold, so we loop back to 0, and so on. And for a fixed threshold, for our selection of threshold, we can essentially compute the probabilities of transitioning from state 0 to state D, and we can see that this probability is exactly, based by construction of the threshold, exactly equal to 1 by D+1. And therefore, the probability of looping back to state 0 is 1 minus 1 by D+1, and the rest of the probabilities are 1, because we know that once blocked at each round, we have one round more to being available again. And for this distribution, it's very easy to compute the stationary. For this Markov reward process, it's very easy to compute the stationary distribution. And essentially, by doing that, we can see that this system, this process is at state 0 roughly half of the time, D+1 by 2 D+1. And even though our algorithm starts at state 0, we can see that this system converges exponentially fast to stationarity. And therefore, by this analysis, we have already proved that the probability of being available at any round T is equal to D+1 by 2 D+1, which is roughly half, up to some vanishing in T additive error. And further, for the first factor above, notice that this is exactly, at least the optimal solution divided by the number of rounds times roughly half by our LP analysis. Again, this is up to vanishing in T additive error. And by combining these two results, we have reached the following theorem. So for the algorithm we presented, if opt is the profit's reward, then the expected reward collected by our algorithm is at least roughly half times the expected reward collected by a profit, minus some additive losses due to the mixing of Markov chains and the loss due to the fact that our LP is asymptotically an upper bound. And also, we prove that this multiplicative guarantee, rho of D, this competitive guarantee is the best possible guarantee asymptotically one can achieve against the profit. Now, let us move on to the case of unknown reward distribution. In that case, we assume that the reward distribution is initially unknown to the decision maker. However, the delay D is still known, but the time horizon N is unknown. And further, here we assume that the distribution has bounded support in 0, 1. And notice that in this case, we assume that rewards are not observed while the decision maker is blocked. And the goal here is to bound the regret against the Bayesian policy, meaning the policy which knows the distribution a priori, for n rounds, and the regret is defined as the expected reward collected by A of n, which is the Bayesian algorithm of that we discussed before, minus the expected reward collected by a learning algorithm for n rounds. Now, some definitions, let f hat sub s be the empirical CDF constructed using S samples, and Q hat sub S be the empirical quantile using this distribution, the empirical quantile function. And the natural idea here is that since we do not know the true threshold, we can estimate this using samples. And this is what we do. So the algorithm in that case is also natural. So at each round, if the resource is available, first we construct the empirical distribution f hat using n sub t samples, which is the number of samples observed so far, which is random. We set a threshold tau hat, which is the 1 minus 1 by d plus 1 empirical quantile. And then we observe the reward. And if the reward is greater or equal to the estimated threshold, then we collect the reward and make the resource unavailable for the subsequent D rounds. Otherwise, we skip on the reward. And if the resource is not available on the first place, then we skip the round without even observing the realization. Now, let us analyze the regret of this algorithm. In the first step, we use the compensated coupling technique by Vera and Banerjee. So what we do is that we define a fictitious policy P sub I, which follows the decisions of L, the learning policy, for the first I steps, including I. And after this point, it follows the decisions of A for the rest of the rounds, from rounds I plus 1 to N. And notice that by construction, the Bayesian policy, A, is equal to P sub 0, and the learning policy matches P sub N. And using this definition, then we can essentially, using a telescoping sum, we can decompose the regret as the expectation of the sum over all rounds of P sub I minus 1 minus P sub I of n rounds. Now, given this, notice that for each term of the summation, the expectation of the difference between these two policies, P of I minus 1 and P sub I, is at most the probability that the realization falls between the estimated threshold and the actual threshold. So here's the actual distribution, and let's say that this is the actual threshold used by the Bayesian policy, and this is the empirical distribution, and the empirical threshold can be either before or after the actual threshold. Now, therefore, the second step, in order to bound our regret, is to control this probability. And our first attempt is using the fact that at around I, the learning algorithm collects at least I by d plus 1 samples. And this is because d is deterministic and fixed throughout the process. Now, using this fact and standard concentration results, we can show that the probability that a realization falls between the actual threshold and the estimated threshold is upper bounded up to constant by root d over I times log I, where I is the number of the round. And therefore, using that, we can see that the regret is upper bounded up to constant by root n times d times log n. But this dependence on d is not really necessary. And the reason is that collecting approximately I by d plus 1 samples by round I is a very pessimistic estimate. Now, in order to get around that, what we do is that we recall that algorithm A, the Bayesian algorithm we described before, for this algorithm, the resources available roughly half of the rounds in expectation. And remember, this was the Markov decision process, Markov reward process, modeling this fact. Now, what we do is that we construct an easier version of algorithm A with some threshold tau prime, which is smaller than the actual threshold tau, and therefore this process moves from state 0 to state D more frequently. And what are the properties of this process? First, algorithm B collects less samples than algorithm A in expectation, but still we can prove by the same arguments that this eager version of algorithm A, B, collects order I samples independent of D by round I with high probability. And what we saw is that after roughly log n rounds, the threshold of the learning algorithm, L, is always an overestimated of this threshold tau hat. Now, using this fact, we can see that the observation is that if this is true, then if both L and B are at state 0 and L collects a reward, then B also collects it. And this implies that for I greater or equal to roughly log n rounds, the learning algorithm collects more samples than this Bayesian algorithm, the eager Bayesian algorithm, deterministically. And here is an example. Suppose that both processes start at state 0. In the first reward is accepted by both policies, and then they move back. And then the second reward is rejected by both policies. And the third reward is only accepted by the Bayesian policy. So we have the learning policy gets one extra sample. And notice that at the end of the process, in the worst case, the extra samples that B can observe while L is blocked is at most the excess. Now, using this fact, we can prove that the regret is indeed independent of D and is upper bounded up to constants by root n log n. And as we saw, by reducing the problem to a two-arm bounded problem, we can prove that our regret guarantees optimal up to polylogarithmic factors in n and dependence on D. Thank you very much. For more information, please read our paper.